Hi everybody! Today we're going to take a look at some oriented Muscovite plates and the fun experiments that we can do with these, particularly regarding the addition and subtraction of interference colors. Here's an example of these oriented Muscovite plates in ambient lighting. And these are thin rectangular plates that have been specifically oriented to help us understand some of the optical properties of our Muscovite mica. And you can find examples of these for sale at the eBay store, Snellius Minerals. There are other Muscovite mineral products for sale there as well, so just make sure to pick out the right ones for the experiments you'd like to try out. Our last two educational videos have explored different aspects of our Muscovite mica. Today we'll try and be brief with our background information about Muscovite mica. For a deeper dive into the structure and optics of our Muscovite mica, check out the video Snellius Minerals Oriented Muscovite Sheet. Or, for a deeper dive into interference colors, check out the video Snellius Minerals Variable Thickness Muscovite Sheet. Now on to our background information. Our minerals are defined by their chemistry and structure. This chemistry and structure in turn gives rise to the crystallography that we see at the macro scale, as well as the optical properties that we'll end up seeing. Our muscovite is defined by its chemistry and structure. Its chemistry consists of potassium, aluminum, silicon, oxygen, and hydroxide, arranged together in the structure of a TOT dioctahedral sheet silicate with interlayer potassium. Here's an example of a greatly simplified structure model for our muscovite. The structure of our muscovite makes it highly anisotropic with respect to its physical properties. And the bonding within our TOT layers is much stronger than the potassium bonds that hold those layers together. As such, our muscovite mica ends up with a perfect cleavage plane that only cuts the C crystallographic axis, and this cleavage plane will help us to orient our muscovite sample crystallographically. Back out to the big picture, we talked a bit about the chemistry and structure of our muscovite, and taking a closer look at our oriented muscovite plates, the main crystallographic feature that we're seeing here is that cleavage plane. That's why these muscovite plates are so perfectly flat, because of that perfect cleavage that only cuts the C crystallographic axis. As these muscovite plates are lying on that cleavage surface, that lets us know that we're looking onto the plane of the A and B crystallographic axes. However, we don't know exactly where in this plane those A and B crystallographic axes lie. We're going to also have to bring in some information from optical mineralogy in order to place those axes appropriately. Once again, back out to the big picture, now that we've talked about our chemistry and structure as well as our crystallography, let's now investigate the optical properties of our muscovite, and to do that we want to think about the optical indicatrix, which is a three-dimensional representation of the refractive indices of our substance. And in the case of our biaxial muscovite, the shape is a triaxial ellipsoid. In many of the more symmetric crystal systems, the axes of our optical indicatrix and our crystallographic axes align. However, because muscovite is monoclinic, only one of our crystallographic axes and the axes of our optical indicatrix will. The B crystallographic axis of our muscovite aligns with the Z direction of our optical indicatrix. Our C crystallographic axis is inclined anywhere from 0 to 5 degrees to the X direction of our optical indicatrix, and our A crystallographic axis is inclined anywhere from 1 to 3 degrees with respect to our Y direction through our optical indicatrix. We know from earlier that the cleavage of our muscovite only cuts the C crystallographic axis, and so when looking onto one of these cleavage surfaces, the view of our optical indicatrix that is closest to what we'll actually see is this one. We'll focus on this view now, but do note that we're 1 to 3 degrees away from where we should be. So technically the view we'd actually have of our optical indicatrix is a bit more like this. You can think of this as a rotation of the optical indicatrix by 1 to 3 degrees, depending upon that angle between our A crystallographic axis and the Y direction of our optical indicatrix. The shape of our optical indicatrix in this view has changed ever so slightly as well. instead of refractive index beta, here we have refractive index alpha prime, which is a value somewhere between refractive indices alpha and beta. As we've only rotated the optical indicatrix between 1 and 3 degrees, this value of alpha prime is going to be very, very close to beta. Let's also take into consideration where our optic axes will be in this diagram, here represented by 2 stars. And further note that the interference figure that we generate with this view of our optical indicatrix is almost an acute bisectrix figure, or a BXA figure. Once again, we're 1 to 3 degrees away from this view, just depending on how far we've actually rotated our optical indicatrix. We've reviewed the chemistry and structure of our muscovite, along with a bit of the crystallography and the theory behind our optical properties. Now let's examine our oriented muscovite plates with a polariscope and see if we can use some of our optical properties to help us fully understand the crystallographic orientation of these plates. Here we have our oriented muscovite plates viewed in plane polarized light. We'll now bring in our upper polarizer so that we're viewing our plates with crossed polarizers. What we're seeing here are interference colors, and our plates have different interference colors in this case because they are different thicknesses. We'll talk more about these interference colors in a moment. However, right now, the piece of information we're looking for is going to be gained by generating an interference figure. In order to generate this interference figure, we bring in a converging lens to our polariscope setup. Here's the interference figure for our upper plate, and now we can switch over and take a look at the interference figure for our lower plate. And we now have enough information to fully understand the orientation of our muscovite plates. Let's go back out to the theory for a moment to explain how. We know where our optic axes will be located in our optical indicatrix, here represented by 2 stars. And our optic axes are going to be the melotopes in our almost BXA interference figure. We are looking onto the cleavage plane of our muscovite plates. And we know the location of the optic axes. We now know the location of the A, B, and C crystallographic axes of our muscovite. There's also a more in-depth treatment of what's going on here in the video, Snellius Minerals Oriented Muscovite Mica Sheet. And moving forward, the interference figure for our lower muscovite plate also allows us to orient it appropriately. Now that we understand the orientation of our muscovite plates, let's go back and focus a little more on interference colors. We'll start back out at our view of our optical indicatrix. And while our optical indicatrix is a 3-dimensional representation of our refractive indices of our substance, if we're only taking one view through a substance, all we have to think about is a plane. In the case of our muscovite plates, the gamma alpha prime plane. With this knowledge, if we return to a view of our oriented muscovite plates in plane polarized light, we can think about how our plane polarized light is going to interact with our muscovite plates. Our plane polarized light in this view is vibrating in a north-south direction. When it interacts with our muscovite crystal, it's going to split into 2 beams that vibrate in mutually perpendicular directions associated with refractive index gamma and refractive index alpha prime. These 2 beams are going to travel through our crystal at different speeds. And so the difference between their travel time through the crystal is going to be based on the difference in refractive indices, also known as the birefringence, as well as the thickness of our sample. The interference color that we see when we bring in our upper polarizer is a result of the difference in travel time of our 2 rays. This difference is also known as the path difference, or also a retardation. We explored the mathematics behind this in depth in the video Snellius Minerals Variable Thickness Muscovite Sheet, and we'll have a quick review of this here. Conceptually, our interference color is going to be based on the thickness of our sample and the birefringence of our sample in this particular view. So delta, which is the path difference, is equal to d, the thickness of our sample, multiplied by n2 minus n1, which is our birefringence, the difference in refractive indices. Right now, the one variable we know for sure is the birefringence of our muscovite mica in this view. So in this equation, we can replace N2 minus N1 with gamma minus alpha prime for our Muscovite mica. For refractive indices gamma and alpha prime, we'll use the values of 1.599 and 1.590 respectively. There is some variability here. The difference between gamma and alpha prime is then 0.009. And for this particular orientation of our muscovite, we now see the relationship between the thickness of our sample and interference color. In our previous video on variable thickness muscovite sheets, we used our interference color and a tool known as the Michel Levy Color Chart in order to calculate the thickness of the different areas of our variable thickness muscovite sheet. We'll do some different experiments with our oriented muscovite plates today, and we'll come back around to this at the end. Let's first see how our oriented muscovite plates interact with one another. We are currently viewing our oriented muscovite plates with crossed polarizers. Let's see what happens when we put our oriented muscovite plates perpendicular to one another with crossed polarizers. Our interference colors are currently a light green and a purple color, and by crossing our mica plates perpendicular to one another, we end up with a gray interference color in the center. There has to be something interesting going on here for our light green and purple to add to gray. Now let's bring in our converging lens to investigate our interference figures. Our interference figures where our mica plates do not overlap haven't really changed at all from before. However, where we have our plates overlapping, we see this totally different and kind of complicated interference figure. I'm thinking I'm going to need a real physicist to help me out with that one. That one there is, that's complicated. In order to understand what's going on here with the interactions of our oriented muscovite plates, we're going to have to go back out to the theory. But before we do that, let's also take a look at what happens when we orient our muscovite plates parallel to one another. Here, our light green and purple interference colors become a dark green where our plates overlap. So far, not as strange as the behavior we saw when our plates were perpendicular to one another. Now let's bring in our converging lens in order to check out the interference figures in this view. Once again, where our plates do not overlap, there isn't any change in our interference figure. And where our plates do overlap, things become a bit more complicated. However, this interference figure that we see will actually be fairly simple to explain. We've now gone through the main experiments that I wanted to show off with our oriented muscovite plates. Let's go back to the theory to figure out what was actually going on here. We've got our two oriented muscovite plates that display distinct interference colors when viewed with crossed polarizers. And we can understand the orientation of these plates with a combination of our optics and crystallography. Using that information, we know that both plates are oriented in the same fashion at this moment. And when investigating the optics of these plates, we're going to be looking at the gamma alpha prime plane of our optical indicatrix. We should try and spot each of these interference colors on our Michel Levy Color Chart. This would allow us to identify the path difference for each of our plates, and then we could also calculate the thickness of each plate if we so desired using this equation. Our interference colors for our oriented muscovite plates line up here on our Michel Levy Color Chart with values for path differences of 1330 and 1130 respectively. Our almost BXA interference figures help us to understand the order of our interference color. Let's zoom in on one of our almost BXA interference figures to learn more. The melatope of our almost BXA interference figure is the same as the start of our Michel Levy Color Chart. We then work our way through the isochromes until we get to the middle of our BXA interference figure, which is the same color as our interference color. Now that we have an idea of where our interference colors lie on our Michel Levy Color Chart and the path differences that they represent, we're ready to understand how these two oriented muscovite plates interact with one another. We'll first superimpose onto our plates an image of our refractive indices in this plane. Our larger refractive index gamma is associated with the longer direction of our oriented Muscovite plates, and if these were natural mineral growth patterns, we would refer to these as length slow, meaning that the longer direction of our crystal is associated with our larger refractive index, and therefore light traveling along our crystal in this direction will be slower, giving rise to the terminology length slow. For our oriented Muscovite plates, I haven't cut these all in the same manner, so sometimes they could also be length fast. The plates in our demonstration today just happen to be length slow. When we cross our oriented Muscovite plates perpendicular to one another, our refractive indices end up at odds with one another. The slow direction of one of our oriented Muscovite plates is aligned with the fast direction of our other plate. What ends up happening where our plates overlap perpendicular to one another is actually fairly simple. The new interference color that we see ends up just being the difference between our two previous interference colors. In the case of these particular plates, where our interference colors yielded path differences of 1330 nanometers and 1130 nanometers, the difference between these two path differences will be 200 nanometers, corresponding with a light gray interference color. And that's exactly what we see with this experiment. Let's now figure out what happens when we have our plates oriented parallel to one another. When we place our oriented Muscovite plates parallel with one another, our refractive indices align for our plates. Gamma is aligned with gamma and alpha prime with alpha prime. And so in this instance, our interference colors and path differences will actually add with one another. You can sort of think of this as we just have a much thicker mica sheet. Going back to our Michel Levy Color Chart, our path differences of 1330 and 1130 add with one another to 2460. Which ends up being way off this particular Michel Levy Color Chart. However, the pattern that we see with our interference colors here continues on for quite some time until we eventually reach a thickness of material where the interference color just starts to look like white light. We can tell we're at this very high order interference color, however, by taking a look at our interference figure for our overlapping Muscovite plates. Zooming in on our interference figure, we can see that there are quite a few isochromes between the center of our almost BXA interference figure and our melatope. Also, this almost BXA interference figure is just the same as one you'd see for a thicker piece of Muscovite mica. The interference figure that actually causes some theoretical complication for us is when we have our oriented Muscovite mica plates perpendicular to one another. There's a whole bunch of additions and subtractions going on there that I don't feel comfortable trying to explain. I'm going to need a real physicist for that one, so yeah, we'll let that one lie. We've now gone through all of the experiments that just use our oriented Muscovite mica plates that I wanted to show off, so hooray! But I also wanted to mention that these carefully oriented mineral plates actually have practical applications as well. If you've used a petrographic microscope in the past, you're probably aware that one of the accessory plates is a mica plate, also known as a quarter wavelength plate. These accessory plates are helpful in determining the optic sign of unknown materials, which tells us about the relationship between our refractive indices. These oriented Muscovite plates are most definitely not quarter wavelength plates, but we can use them in a similar manner to get a theoretical understanding of how the determination of optic sign works. One last experiment for today. Here we have a slice of beryl we're viewing down the C crystallographic axis. We are currently viewing our beryl in plain polarized light. We'll now bring in our upper polarizer and view our sample with crossed polarizers. The beryl displays some low first order interference colors in this view. And we can bring in a converging lens to generate an interference figure. We see our interference figure is a nice uniaxial optic axis interference figure, meaning we're looking down the optic axis of our beryl and the C crystallographic axis. We'll now reset everything and show off what our oriented Muscovite plate can do for us in helping us to determine the optic sign of our beryl. We are back to viewing things in plain polarized light, and we've added in our oriented Muscovite plate. Our oriented Muscovite plate in this instance is length slow. In plain polarized light, adding on our oriented Muscovite plate doesn't really do anything. However, when we bring in our upper polarizer to view this setup with crossed polarizers, we can see that the interference colors of our beryl and Muscovite plate are adding and subtracting from one another. We could then determine if our beryl was length slow or length fast. However, our beryl today is not oriented appropriately to allow us to make such a determination. We'll save that for a later video. With our beryl in this particular orientation, however, we can determine optic sign. We do this by bringing in our converging lens, and from the resulting interference figure, we can actually determine optic sign. We'll get into this in much greater depth in a later video, but optic sign for our uniaxial beryl is going to be the relationship between refractive index omega and epsilon. If refractive index epsilon is greater than refractive index omega, the optic sign is positive. If refractive index omega is greater than refractive index epsilon, the optic sign is negative. In order to figure out what's going on here, we first want to go back to our uniaxial optic axis interference figure that we generated earlier with our beryl. We'll zoom in a bit here. And what I want you to notice when we transition to the image of our interference figure where the Muscovite plate is added is where do our interference colors add and subtract from one another. We'll do that transition a couple more times. And without going much further down this very deep rabbit hole, the locations in this interference figure where our interference colors add and subtract actually tell us that our beryl is uniaxial negative. We'll talk about this in much greater detail in a later video. Today I just wanted to show you that these oriented Muscovite plates actually do have some other uses. We've covered pretty much everything I wanted to talk about with our oriented Muscovite plates for today. So let's now do a brief review of everything we looked at today and wrap things up. Our minerals are defined by their chemistry and structure, and today we did a brief review of the chemistry and structure of Muscovite. We first examined a simplified structure model for our Muscovite. The weaker potassium to TOT bonds in our Muscovite yields a perfect cleavage plane that only cuts the C crystallographic axis. And so when looking at the crystallography of our oriented Muscovite plates, that cleavage plane helps us to figure out the orientation of these plates. However, it does not provide sufficient information to fully orient our Muscovite plates. For that, we also have to examine the optics. We first reviewed the theory behind our optical indicatrix for Muscovite, and then examined our oriented Muscovite plates with a polariscope in order to generate interference figures. The cleavage of our Muscovite plates, coupled with the location of the melotopes in our almost BXA interference figures, allow us to fully understand the orientation of these plates. Now that we understood the orientation of our Muscovite plates, we focused a bit more on interference colors and the Michel Levy Color Chart. We figured out the path difference for the interference color shown by each of our oriented Muscovite plates, and how the almost BXA interference figures can help us figure out the order of our interference color. The unique experiments today really revolved around how our oriented Muscovite mica plates interact with one another. When we overlap these plates so that they're perpendicular to one another, our refractive indices are at odds with one another. Gamma of one plate is aligned with alpha prime of the other, and vice versa. Because of this, the interference color that we see where these plates overlap is the difference between the interference colors of our two oriented Muscovite plates. When we take our oriented Muscovite plates and overlap them so they're parallel to one another, the refractive indices of both our plates align with one another. Because of this, the interference color that we see where these two plates overlap is the sum of our individual interference colors for each plate. And unfortunately for us, this plots well off our current Michel Levy Color Chart. Our interference figure for our plates that overlap parallel to one another is the same as the almost BXA interference figure we just see for a thicker piece of muscovite. However, the interference figure for where we have our oriented muscovite sheets perpendicular to one another is much more complicated. So complicated, I'm going to leave that one alone. We also explored how having a known oriented muscovite plate can help us determine things like optic sign for unknown samples. In particular, we looked at a beryl specimen and how our oriented muscovite plate can be used as an accessory plate in order to generate a whole new type of interference figure. One that allows us to determine optic sign based on addition and subtraction of interference colors. If you'd like to pick up your own oriented muscovite plates, you can do so at the eBay store, Snellius Minerals. We have a variety of muscovite products for sale, so just make sure to pick out the right ones for your purpose. If you have any questions or comments, feel free to reach out at the email snelliusminerals@gmail.com. Here are the references that I consulted in putting together today's video. Thanks again for watching, and have a great day!